Alright, so here's an example for class 13 for ME370, and it is a problem 384 out of the textbook and 387. So the cantilever bar in the figure is made of a ductile material and is statically loaded with 250 pounds in the y direction and nothing in the x and z direction. Analyze the stress situation at the small diameter right there at the shoulder at A by obtaining the following information. Determine the precise location of the critical stress element at the cross section of A, and sketch the critical stress element and determine magnitudes and directions for all the stresses acting on it. Transverse shear may be neglected if you can justify this decision. And for the critical stress element, determine the principal stresses and the maximum shear stress, and then repeat this for brittle material requiring the inclusion of the stress concentration fillet radius. So let's do this one right here, and we're going to pick cast gray iron out of the book, and so that we do have to worry about stress concentration, and so we'll look up which this is. Now, did I change this problem? I had thought about changing this problem, but I did not change this problem. I kept it the same. So we're going to look at this location right here. From the free body diagram, which we could probably skip, but we're going to do it anyway. Looking at it from the side in the XY plane right here. Right, and they said that they're going to have 250 pounds coming upwards, like that right there. So we have 250 pounds right here, and it appears to me that we're going to have 9 plus 2 is the distance that we have right here, so 11. Is that what I did in my thingy? Yep. And so we're going to have a reaction that's coming downwards, Ry. Nothing in the x direction, so we don't even need to draw that in. And this goes counterclockwise, so this one, the reaction on there is in that direction. Sum of the moments about z is equal to 0. So reaction, z, I'm thinking about starting to include an r right there so you know that this is a variable. It's not that. This is its own thing, right? So we can put it up right there. And that's going to be negative right here because that's going this way. We define clockwise, counterclockwise as positive. So we have plus our 250 times our 11 equals 0. So mz is going to be 2,750 inch-pounds. If we take a look, we could, let me see, I'll draw it over here, just quietly right here, right, boom. This would be the xz direction. You see, there's no forces. You don't see any forces right here, right, because the y is coming up out of the page. Much more interesting thing if we put x and the z in there, but this problem didn't do it. Right, so we're going to predict that the worst stress element is going to be right here or right here, right? That's where the bending is going to take place, and there's no axial. We do want to get the torsion onto this, and once again, you know, we could, if we were going to be honest with ourselves, we could be saying that there you go, YZ, that like it's kind of obvious that what the answer would be, but I don't want you just depending on that because you notice that you might have gotten it wrong previously, right? There's the RY that was disgusting. And a moment is going to be going counterclockwise. That's about x, and then this distance is 12 inches. Sum of the moments about x equal there, and maybe we put the r right in there. Because I forgot that, and then so the reaction moment, and then minus 250 times 12 equals 0. So mx is equal to, what is that? It's 3,000 inch-pounds, right? And so the justification that we can ignore this, right, is if we take a look at the cross-section right here, and we take an element here, and an element here, an element here, and an element here, we're looking at compression right here, right? You can almost just see that this force is going to be going right here. It's going to compress a point at the top. So there's going to be tension here, right? So there's compression here, and there's tension here. But that force is coming upwards across the thing. So it's going to have transverse shear here and transverse shear here. But it's going to be 0 here and here. So we can ignore transverse shear. That's what they're saying. Is you can neglect it if you can justify this decision. Right, that's our justification of the decision, if we're following this. Now we're going to get the stress concentration of that point right there, which is going to be flipped through here. It's going to be similar to this, but this is axial. We want to look at, this is torsional, and this one is bending right here, right? So we have both of these conditions. We're going to have bending, and we're going to have torsional. So, and we're going to, and these are based on the smaller of the diameters right here, right? Same thing down for here. This is based on the smaller of the diameters. So let's figure out what that, what the I is going to be is pi over 64 times d fourthed. And the diameter right here is, that's not the diameter. This is the diameter is 1, right? It's 1 inch diameter. So pi over 64, 1 to the 4th, ends up being 4.909 e minus 2. We end up with that number a lot, don't we? And then j is just going to be 2 times I, which ends up being 9.817 e minus 2 inches fourthed. So the nominal stresses right here is going to be mc over I, and tau is going to be tr over j. And so we get 2750, 1 over 2, 4.909 e minus 2. And that comes out to be, I'll turn it into KSI just by looking at it and go, oh, KSI. And that's going to be both tension and compression. But it turns out most things, if they're going to break, they actually break because of tension and not because of compression. We'll actually see for this cast iron, we'll see in a second that that's going to be the case. So we could say that this is T and C, depending on which point that you talk about, right? It's compression up here, tension down here. And this guy, he is 3,000, 1 over 2, and then 9.817 e minus 2, and we are 15.28 KSI. Neither tension or compression, right? So depends on which point that you're taking a look at, but you know, like if we're looking down onto the thing, it would be, let's see, X and Z. It'd be in compression if we're looking down onto the thing. And the torsion is going this way, so across that face. Right there. That's what we would, this would be what a stress element would look like without the stress concentrations, right? So this guy is 28 KSI, and this is 15.3 KSI. All right. Now we need to look up and find out what the stress concentrations are going to be at this spot right here. We need the different diameters. We need the ratio of the diameters right here, and we need the radius divided by the diameter, and the same thing down for both of them. So let's take a look at what big D over little d is going to be. That's going to be 1.5 divided by 1. Well, I can do that in my head. That's 1.5. And the radius here, they're saying it's 1/8 inch, right? So that's going to be R over D of 0.125 divided by D, which is 1, and I can do that in my head too. Right, so those are the two things we're going to look up. We need to find KT, that's going to be for the bending, and KTS, that's for shear, right in there. And you'll see that they're even labeled that way. So let's start with the bending one. It's easy to get these. Oops, what happened? I think I just turned off the monitor. See, how bad is that going to make everything here? I wonder if it's still going to record the thing. I wonder if that looked like anything to you. Maybe it didn't. I don't know. All right. I hit the switch, unfortunately, with the keyboard. Let's get this guy out of the way. Okay. So down here, taking a look at this, we have 1.5, which is lucky for us. We have that as one of our choices, right? And we have 0.125, which is, there's 0.1, here's 0.15, so here's 0.125 right here. And the intersection of there is really, really close to 1.6. In fact, we could really, really, really zoom in, and I just messed that thing up right there. But if we really zoom in, it's a little bit below. It's just ever so slightly below. So I call it 1.58. 1.58. And then if we go to the other one right here, this one is for the torsion, right? So you got to be careful. You notice that it's a KTS. That's right in there, right? So once again we go to they don't have 1.5. They have 1.3 and 2, so it's somewhere in between there, and you can see that it's right in here. And once again, I've written in my book way too often, so I said that that's 1.36. Boy, that's awful. That's okay. But this is 1.2, right? And as you try to in there, 1.36 is the best I could estimate as part of this. Now, I have made this in Excel and really, really zoomed into there, but 1.36, right? So you can see that 1.2 is right here. 1.3 is right in there. So 1.36, yeah, maybe. It's really close. I'm going to go 1.38 maybe. It's hard to say. It should be pretty close to the 1.33. Anyway, I'll stick with the numbers that I had right here, but we could argue about this and try to get a finer point, but it's best we look at it. So what they had here, okay, so now we have the sigma max is going to be the KT times the nominal, and the tau max is the KTS times the nominal. Oops. And so 1.58 times our 28, and we're left with, where'd you do the math? 44.26 KSI. And here we have 1.36 times our 15.28, and we're left with 20.78 KSI. Now, we need to convert these into a number that's comparable. And what we're deciding to do, and we have to be careful on this, is we're going to use the principal stresses as the means. We're going to find out pretty soon that that's not a really good method of doing the thing. So, but now, let's take a look at the, well, first off, let me take a look at the strength numbers. I told you that it was ASTM gray cast iron. So if we go through our book and take a look at the only place where there's any cast iron is right here in table A24. For some reason I'm circling the book here. This is gray cast iron and ASTM, and the ASTM number is 60 right here. And you see it has tensile strength of 62.5, but compressive strength of 187.5. So we want to take a look at the safety factor. It's going to break in tension before it breaks in compression. And we'll talk about this some more, that cast iron is one of the type, and many brittle materials possess this behavior, that they're stronger in compression than they are in tension. So we're going to use 62.5. So when we're taking a look at our stress element that we're going to pick for this thing, we're actually going to be looking at the one that's on the bottom of this, because that's where it's at tension. So I draw that thing in here. So if we're looking at that stress element, so in that case, by the way, we're looking at the underside of it. That's the direction that the Z would be going. You can see how here, this one we're looking at the top, here we're looking at the bottom. It doesn't really matter, but we've applied the stress concentrations of 44.26, and I believe the shear is still going to go in that direction right there onto this. Not that it's going to matter. And so this is the 20.78 KSI. So if we're going to do the principal stresses onto the thing, let's take a look at that. I'll go C equals, and that's just going to be the center of the thing. So 44.26 divided by 2. I should plot these out. So this is 44.26, this face, and that's counterclockwise. So if I went like 10, 20, 30, 40, 10, 20, like that, this would be 50. We're plotting something down like right in there, and then we go 10, 20, and we're plotting something like right in there. And if we take a line in between here, and then of course I probably did a really lousy job of plotting that, but let's try to do this anyway. I get my compass out. Yeah, I didn't do a great job plotting it. So, but like that right there. And what we're going to find is now we're going to have like a little tiny more circles inside this. If we're going to make it complete with our 3D more circle, but it's in this case it's not 100% necessary, right? So we'd have a circle like that, except that that would be touching right there, and then we would have a circle similar to this, right to here, to there. Let's see. But I still doing it wrong. Become a better plotter. Okay. So, whoa, what happened there? I think I just moved it. Yeah, like that. You get the idea, right? And so there's going to be your principal stresses right here, and right here. This is that first principal stress, second principal stress, third principal stress. If we cared about the thing, here would also be where the tau abs max is going to be. But what we mostly care about is plotting what the this difference is. This is the guy that we're going to care about. -20.78. And this is the 0 and 20.78. All right, so that's fully labeled. The C is going to be that 44.26, and it turns out to be 22.13. Could have done it in my head. The radius of the thing we'll pick is going to be right there. Square root of 22.13 is this leg right here, right? Because that's where C is. And this is the 20.78 squared. And when we get that, we get 30.36. And so the principal stress, C plus R, is going to be 22.130 plus 30.36, and we're left with a 52.49. If we wanted the other ones, we would say that second principal stress is 0 because of the way that this thing lands, and third principal stress is C minus R, and that just ends up to be negative 8.23 KSI. But now we want to get the safety factor. We want the ultimate intention divided by the principal stress here. And that's 62.5 that we looked up, right, divided by our 52.49. So we've been able to combine them into completely normal stresses, and you get 1.18, and that's the answer. And only 2 decimal places. So, taking a look at the big picture, that's the whole thing right there, right? We have now walked through an entire problem and gotten to a principal stress and then a safety factor. We've assessed. It doesn't have much of a margin right there compared to for braking. So the end. 22 minutes.